Hi kids, this is discussion 7-1 on energy transfer, state changes, and the difference between exo and endothermic processes. All right, so first let's talk about what energy is. The fancy schmancy scientific definition is that energy is the capacity to do work or produce heat. You'll learn about what work means in the scientific sense if you take physics. So what is heat? Heat is thermal energy that flows between a system and its surroundings. And we'll talk about what those things mean on the next slide, or a couple slides. So the unit of heat will be either joules, which is represented with a capital J, or kilojoules, which is a lowercase k with the uppercase J, so kJ. Heat will flow, and it will always flow from a warm object to a colder object. So if you have two objects in proximity to each other, if one is warmer than the other, the heat will flow from the warm object to the cold object. So a good example of that is putting an ice cube in a glass of water. So when you put an ice cube in a glass of room temperature water, the water is warmer than the ice cube. So heat will flow out of the water into the ice cube, which causes the temperature of the water to go down. It causes the temperature of the ice cube to go up, so the ice cube begins to melt. Then, once you have your cold water, if the air around the glass is warm, then that means the air is warmer than the water in the glass. So heat will flow from the air into the glass. That causes the temperature of the water to go up, and it causes the temperature of the air to go around the glass to go down. So the water vapor in the air near your glass will condense as a liquid and collects on the outside of your glass. So heat always flows, and it always flows from warm to cool. Now, if you need to convert between joules and kilojoules, of course, you should know by now that there are 1,000 joules in 1 kilojoule. And there are 1,000 seconds in 1 kilosecond. And there are 1,000 meters in 1 kilometer. And there are 1,000 anythings in 1 kilo anything. All right, so let's talk about temperature versus heat. Heat and temperature are not the same thing. They are different. Temperature is a measure of the average kinetic energy of the particles. So as you heat a sample, they start to move faster. They have more kinetic energy. Heat is the energy content in a system. Temperature is measured in degrees. Degrees Fahrenheit, degrees Celsius, kelvins. Heat is measured in joules, different units for different properties. Temperature is an intensive property, and heat is an extensive property. So remember back from Unit 2, an intensive property is a property that is independent of sample size. In other words, if you add more material, it doesn't change the property. An extensive property is the opposite. An extensive property is dependent on sample size. So as you add more stuff, the property will change. So temperature is an intensive property because adding more stuff doesn't change the temperature. Things like mass are extensive properties because if you add more stuff, the mass goes up. But even though heat and temperature are different, they are related to one another. Because if an object gains heat, its temperature will increase, and if an object loses heat, its temperature will decrease. So the example we talked about with the glass of water, the water gets cold when you put the ice cube in because heat is leaving the water, which causes the temperature of the water to go down. All right, so now let's talk about system versus surroundings. The system is the thing that's happening. It could be either a chemical change or a physical change, but your system is the process. The surroundings are the area where that process is occurring. So think of a fireplace. The system is the chemical reaction of the fire burning in the fireplace. The surroundings is the room that fireplace is in. So our chemical reaction will always be the system. The area where that chemical reaction is happening is the surroundings. Now, even if it's a physical change, like let's say dissolving salt in water. If you're dissolving a salt, not table salt, but a salt, an ionic compound in water, you could experience a temperature change. The system in that case would be the salt, and the surroundings would be the water. So remember, our surroundings are not always going to be air. So now let's talk about endo and exothermic changes. Thermic refers to thermal energy or heat. Endo means in, and exo means out. So an endothermic change is one in which heat must go into the system. And an exothermic change is one in which heat goes out. Another use of endo and exo refers to skeletons, right? Like vertebrate animals have endoskeletons because our skeletons are inside our bodies, and insects have exoskeletons because their skeletons are on the outside. So an exothermic change, energy out, is a change in which energy is released to the surroundings. That means the system will lose heat, but the surroundings will gain heat. So in an exothermic change, the temperature of the surroundings will increase because heat is being given off by the system. If heat is being given off by the system, that means that heat is being absorbed by the surroundings. So the example of the fireplace is an example of an exothermic change. The system is the fire burning, right? The fire burning gives heat to the room, so the room gains the heat and its temperature goes up. For an endothermic change, endothermic means the change will require energy. So energy will be absorbed from the surroundings. So in an endothermic change, the temperature of the surroundings will decrease because the heat energy is being taken from them. All right, so now let's talk about changes of state. Let me bounce around here. All right, so remember our three states of matter are solid, liquid, and gas. All right, remember, in a solid, the particles can't move in relation to one another. They just kind of vibrate in place. If you add enough heat, they begin to move faster so they can separate. They move a little bit faster in a liquid. And if you heat them more, they begin to move faster and faster and faster. That means solid is the lowest energy phase and gas is the highest energy phase. So if the particles begin moving faster or more quickly during the change, well, you can infer that they picked up energy along the way. If they gained energy, that means the change is endothermic because endo means energy goes in. If the particles start moving more slowly during the change, well, if you start fast and end up slow, you can infer that you lost energy. And if you lose energy, if energy goes out, that change would be exothermic. So here are examples of all the state changes you're responsible for. All right, so let's look at melting. Melting goes from solid to liquid. The particles in a solid move more slowly than they do in a liquid. They started moving faster, which means energy was gained. And if energy was gained, the change is endothermic. Think about it this way. If you want to melt an ice cube, you got to put it in a warmer environment, right? Well, if you put an ice cube in a warmer environment, that ice cube will absorb heat from the environment, right? Or think about it this way. If you want to melt an ice cube, you got to put it in a hot area, right? Well, if you're hot, that means you gain heat. So freezing is the opposite. Freezing goes from liquid to solid, right? So we start with faster particles and go to slower particles. Since they go from fast to slow, you can infer that energy was lost. So freezing is exothermic. Think of it this way. If you want to freeze water, don't you got to make it colder? And if you make something colder, doesn't that mean it lost heat? And if you lost heat, doesn't that mean the change is exothermic? All right, so pause the video for a minute. See if you can work out for the rest of the phase changes if they're endo or exothermic. And then come back to get the solutions. Okay, so boiling, also known as evaporation, is liquid to gas. Gas particles are faster. They increase in speed, so that tells you it's endothermic. Think about it this way. If you want to boil water, don't you got to put a flame under it and put energy into it? So the opposite of evaporation is condensation. You're going from fast gas particles to slower liquid particles. That infers a loss of energy, so that means exothermic. But if you want to condense a liquid from a gas, don't you have to cool that gas? And if you cool that gas, isn't that the same thing as taking heat away? Oh yeah. All right, finally, sublimation and deposition. Sublimation, you may recall, is going from a solid directly to a gas without becoming a liquid in between. But everything still follows through because solid particles are still slower than gas particles. They started moving faster, so that makes it an endothermic change. And deposition, which is the opposite of sublimation, is gas to solid. You're going from fast to slow. Energy was lost, so it's exothermic. All right, now let's talk about molar heat. Molar heat of fusion and molar heat of vaporization is just the amount of heat per mole it takes to either fuse or vaporize a compound. Now, when we talk about fusion, the word fusion just means to come together. So when a liquid freezes, the molecules or atoms in it essentially fuse together. So the molar heat of fusion is the amount of energy that is required or released when 1 mole of a substance melts or freezes. So in this discussion, we've already talked about how if something loses heat, its temperature decreases. Well, molar heat is the specific amount of heat that needs to be lost to freeze or the heat to gain to melt. So molar heat of vaporization is the same thing, but instead of being melting and freezing, it's the amount of heat required or released when 1 mole of a substance evaporates or condenses. The units of molar heat, it's heat per mole, so it'll either be joules, which is heat per mole, or kilojoules, which is heat per mole. Now, sometimes amounts are not measured in moles, they'll be measured in grams. So really, molar heat of fusion is just energy per amount. So if your amounts are measured in grams, it'll still be joules over grams or kilojoules over grams. So let's look at a couple of examples here. This one says a substance has a molar heat of vaporization of 498.2 joules per mole. How much energy in joules is required to vaporize 35.2 grams of this substance if the molar mass is 132.35? All right, so the first thing we got to think about is our conversion factors. Well, what this says, it's the number of joules per mole. Well, if I know how many moles I have, I would just have to multiply to find out how many joules it is. But we are given a mass in grams. We have to convert that mass in grams to moles. We just spent a month learning how to do that. So you better know how to do it. All right. So first conversion factor we're going to use in step 1 is the molar mass to convert this mass into moles using the molar mass. This is 132.35 grams per mole. So the conversion factor is 1 mole equals 132.35 grams. Once we know the number of moles, we can use the molar heat as a conversion factor to find the number of joules. So that would say 1 mole equals 498.2 joules, because the unit is the number of joules per every 1 mole. So to solve, of course, we need a fence. Because we have 2 conversions, I need a fence with space for 2 conversions. I put my smiley down below. Now, kids are often confused with what goes up here. But remember, we use that smiley face because nothing ever goes down there except the smiley face. So we can never have a fractional unit go down there because let's say we put the molar mass, if grams were up here, moles would have to go down there. And moles can't go down there because nothing ever goes down there. All right, so that means we're going to have to put 35.2 grams up here. Step 1 is use this conversion factor. I put the grams below so they'll cancel. 1 mole, 132.35 grams. Step 2 is this one. 1 mole goes down below, and 498.2 joules goes above. Grams will cancel, moles will cancel, leaving me with joules. It's 132.35 joules when you do the math. That's the answer, so put a box around it. All right, next one says a substance has a heat of fusion. Notice it didn't say molar heat of fusion, because it's not the molar heat, because it's the heat per gram. So it's just the heat of fusion, and it's 102.2 kilojoules per gram. How much energy in kilojoules is required to melt 10 grams? So again, think of molar heat, or think of heat of fusion in this case, as a conversion factor. In this case, it's the number of kilojoules per every 1 gram. So my conversion factor would be 1 gram equals 102.2 kilojoules. I'm given grams. I got my conversion factor, so I only need a fence with 1 step. Smiley down below, put your 10 grams up above. Plug in your conversion factor, which says that for every 1 gram, there's 102.2 kilojoules, and 102.2 times 10 is 1,022. That's your answer, so put a box around it. Next, I want to talk about the heating curve of water. We talked about this heating curve way back in Unit 2, and what we talked about was each segment. So if we look at the x-axis is heat in kilojoules. So as we move from left to right on the x-axis, we're increasing heat. The y-axis is temperature. So as we increase heat, notice temperature goes up. If we go right to left, we're taking away heat, so temperature goes down. So there are 5 regions of this graph: A, a B, a C, a D, and E. Back in Unit 2, we had to identify what each segment represented. If you recall, segment A, the first diagonal region, was our sample in the solid phase. B is where melting occurs. When melting is occurring, we have both solid and liquid present. Just imagine putting an ice cube on your kitchen counter and letting it melt. It doesn't melt instantaneously. As it melts, you'll see a puddle of water form, but the ice cube will still be in the middle. So we have both phases. Once melting is fully done and the ice cube is gone, our substance is in the liquid phase. So this whole diagonal region here represents the liquid phase. When you add enough heat to a liquid, it will begin to evaporate. So this flat region here represents evaporation. And during evaporation, you have both liquid and gas present. Imagine you're boiling a pot of water. You start to see steam come off the pot before it begins to boil. While it's boiling, you see steam coming off, but there's still water present. So while evaporating is occurring, we have both liquid and gas present. Now, once we've fully evaporated all the sample, E represents our sample in the gas phase. All right, so that was from Unit 2. What we got to know for Unit 7 is how molar heat connects to the graph. So again, as we move in the x-axis, we could determine how much heat. So right there, segment B represents the amount of heat needed to fully melt this thing. So that would be the molar heat of fusion. This whole region of the graph, this entire flat region where evaporating is occurring, notice it's flat, temperature is remaining constant, because the energy going in is separating the molecules and the atoms as opposed to increasing the temperature. So from here to here is a measurable quantity of energy. It's the amount of energy required to vaporize. So that entire region of the graph represents the molar heat of vaporization. Now, going left to right, we're adding heat. So in this direction, melting and evaporating are endothermic. Going right to left, consider it a cooling curve. Going in that direction is condensing and freezing, which are both exothermic. Think about it this way. In this direction, we're adding heat, and adding heat is endo. In this direction, we're removing heat, which is exo. Finally, thermochemical equations. A thermochemical equation is just a balanced chemical equation that also gives you the amount of heat either released or required in the process. So for an exothermic reaction, that means heat is being given off. So for exothermic, you will see heat as a product of the reaction. Here is the heat right here on the product side of the equation. So the thermochemical equations give us new conversion factors to use with dimensional analysis. The conversion factor will be the moles and the energy. So 1 mole of N2 equals 253 kilojoules. 3 moles of H2 equals 253 kilojoules. 2 moles of NH3, which is ammonia, is equal to 253 kilojoules. So we can use the equation as a conversion factor to go between moles of a substance and kilojoules. For an endothermic reaction, heat will be absorbed, so heat will be shown as a reactant. So in this example here, we have liquid water going over to gaseous water. That is an endothermic process, so heat is a reactant. All right, so let's do a couple of examples. Since we've been through Unit 6 and you should know how to use a conversion factor, you might want to try these ones first. So pause the video and come back. If not, use it to learn. All right, so this one says how much heat is given off by the complete reaction of 3.5 moles of nitrogen. So we're given nitrogen and we're asked for heat. So the conversion factor we'll use says that 1 mole of nitrogen equals 253 kilojoules. We only need a fence with one step because we have one conversion factor that can do the job. We put our smiley face down below and our given up above. Then we just have to plug this conversion factor in here, putting the mole down below and the kilojoules up above, causing the moles to cancel and giving us the unit of kilojoules, which is what heat is. And 3.5 times 253 is 866. The unit is kilojoules. That's your answer, so put a box around it. Last example says how many kilojoules of heat are needed to evaporate 36.04 grams of hydrogen. Well, remember, molar heat is always mole. If we're given grams, first thing we got to do is convert to moles. To do that, we use the molar mass, which says 1 mole of water is equal to 18.02 grams. Just to review, 18.02 grams is what 2 moles of hydrogen atoms and 1 mole of oxygen atoms would weigh. But that only gives us moles. Once we have moles, we can use the equation to find out how many kilojoules. That one will be 1 mole of water equals 6.01 kilojoules. So we have to convert to grams, from grams to moles first, and then from moles to kilojoules. I need to make 2 conversions, so I need a fence with 2 steps in it. Put your smiley face down below and put the given amount in the top left. What we are given is 36.04 grams of water. So first things first, we got to convert grams to moles. So grams of water down there, moles of water up there. Once we have that, we can use this one. Put the mole below so they cancel. Kilojoules above. Move me over there. When you do the math, it'll be 36.04 divided by 18.02, which equals 2. 2 times 6.01 is 12.02 kilojoules. That's your answer. So put a box around it. Please make sure you have a good understanding of this topic, because understanding of this topic is instrumental to understanding the next one. Thank you so much for watching, and I will see everybody in class.